Hello everybody. Today I'm going to introduce the paper Training Language Models to Self-Correct via Reinforcement Learning from Google DeepMind. The method is called SCORE, which stands for Self-Correction via Multi-Turn Reinforcement Learning. Basically, this approach shows us a roadmap to instill self-correction behavior in the large language model. First, let's look at the example they provided. Given a problem in the paper, they used a math problem as an example. So the model is supposed to propose the first round solution, which could be incorrect. Then the user gives an instruction as a prompt to encourage the model to correct any mistakes or errors in the first solution. So it should be noted that the prompt is independent from the first solution, but a general one, and the model is then provides a second round solution. All right. So this is a successful self-correction because after prompting without using any information from the first solution, it correctly recognized the mistake or error and gives the correct answer in the second round. Okay, let's formulate it first. So the input to the model is the problem. And the model proposes the first solution and then gave a self-correction prompt that is not dependent on the first solution. The model proposes a second solution. To instill this kind of self-correction behavior, the author studied supervised fine-tuning first. Let's look at what supervised fine-tuning is. A data sample in the training set looks like this. So it has everything: the problem, the first solution, the self-correction prompt, and the second solution. So the problem and the self-correction prompts are the inputs to the model, and the model generates the first solution and the second solution as outputs. And the training objective is to maximize the log likelihood of the output tokens. That is the log probability of y given x. Okay, well then, now let's look at how we construct a dataset like that. To create the dataset, here are two methods. The first is called start. We first need to have a problem dataset with their correct answers, and we pick one from the problem dataset and feed the problem to the off-the-shelf LLM, that is any large language model you can download, like an instruction-tuned model, Llama 3 instruct or Q1 instruct. Then it proposes the first solution. And in the second round, the input to the off-the-shelf LLM is the problem, the first solution, and the self-correction prompt. Then it proposes the second solution. Okay? For the dataset we created that way, there are different possibilities. So if the first solution is incorrect and the second solution is correct, to determine the correctness of the first and second solutions, we need the correct answer from the original dataset so that we can compare them automatically, maybe with an LLM, or simply by comparing the final answers. In this case, if the first solution is wrong and the second solution is right, we put it in the training dataset. And in other cases, maybe both solutions are wrong, or the first is right and the second is wrong, or both are correct, then this dataset doesn't contain behavior we want. So we just discard these cases. And this is how we construct the dataset with method 1, start. With the second method, we simply prompt the off-the-shelf model multiple times with the same problem. So we use sampling methods to generate different solutions. And then we have wrong solutions and correct solutions. And we randomly pair them. We pick a random one from the wrong solution dataset as the solution 1, and the correct solutions dataset as the solution 2. Then we form a training dataset this way. Since we pair the solutions, it is called paired SFT. Okay. Then let's look at how they perform. So table 1 shows the accuracy at the first solution and accuracy at the second solution. It compares these models. One is the base model, which is the off-the-shelf model that is not fine-tuned, and the base model that is fine-tuned with the dataset created with star dataset, and the dataset created with the pair SFT. So as you can see, the base model's performance on the first round is similar to pair SFT method. We also see that the model trained on the star dataset has an improvement in first round accuracy. But this is not what we want. Somehow we increase the accuracy on the first round. However, we can see that the accuracy on the second round for the baseline models is even lower. That means when you prompt the model to correct any errors in the first round solution, it generates a wrong answer sometimes, even though the first round is correct. So it means you gave it a hint that there could be errors and there could be none. Then it corrected something that shouldn't be corrected. And when there are mistakes, it didn't really correct them sometimes. So this is kind of similar to the model trained on star dataset. So the model trained on the star method doesn't really instill self-correction, but rather improve the first round accuracy. Okay. So about the model trained on pair SFT dataset, we indeed get some improvement in the second round accuracy, but it's only minor. So the difference is only 1.8 increase. More specifically, here you can see in the base model, 4.6 of incorrect answers are corrected in the second solution, but 15.8 of correct answers are mistakenly changed into incorrect solutions in the second round. However, with star, we can see that this is even worse. More correct answers became incorrect in the second round. And with pair SFT, this is partially solved, but overall it's still more, there are 5.4 of incorrect answers that became correct answers, and 3.6 correct answers became incorrect answers. Yeah, so here is the author's explanation. On the pair SFT, they said we find the SFT mainly helps by reducing the number of correct problems that are mistakenly changed to incorrect after revision, and does not significantly increase the fraction of incorrect first answers that are correctly repaired. And on the star method, they find a discrepancy. So the author's explanation is that we hypothesize that the discrepancy is due to the data distribution of the two datasets, because the former, the pair SFT, covers a much more diverse space of revision trajectories due to the nature of random pairing. In plain words, the two solutions in the pair SFT are basically irrelevant because they are randomly sampled independently. And while in the star method, they are in the same prompt, so the trajectory is more consistent, and the first and second solutions are highly dependent. To solve this problem, the authors add an experiment that is D star plus and D SFT plus. That means in the original dataset, there are only cases where solution 1 is wrong and solution 2 is correct. And so the models are trained to definitely make corrections in the first solution, even though they could be correct. And the authors want to avoid that kind of behavior. So that means if the first round is correct, then you don't have to correct it in the second response. So they add data samples that are from correct to correct. which means the first solution is correct and the second solution is also correct. Okay, then we have the results in table 2. As you can see, the first round solution accuracy of star is slightly reduced from 55.4 to 53.6. But the second round accuracy is hugely improved. It goes from 41.2 to 54%. So this means the model trained with star dataset was trying to correct all answers in the first round, but now they stopped doing that. If the model thinks the first answer is not wrong, then it doesn't revise it. And for the pair SFT, okay, so in the 2 rounds, their accuracies, you see the accuracy of solution 1 and solution 2 are both increased compared with pair SFT. But now the accuracy of the 2 solutions are equal. So the model gives exact same solutions in the 2 rounds, and we don't see any self-correction behavior. For star, we don't see much improvement either. So star plus. So it's only 0.4% self-correction overall. Here we get the conclusion that SFT doesn't work. It doesn't instill self-correction behavior. And here the authors find 2 different failures of the method. So the one from star is that they find only one mode of correction behavior that makes minor changes. And the model trained with pair SFT has degradation in self-correction abilities due to the distribution shift, because the solutions are independent without correction logic. So the authors say that there are 2 desiderata. One is to directly train on self-generated traces to alleviate distribution mismatch that affect pair SFT. And the second is that self-generated trace employed should prevent collapse to making minor edits during learning. And it should be encouraged to make more significant corrections. Therefore, they need an online reinforcement learning approach. Alright, here comes the reinforce method. We call it reinforce. It is a reinforcement learning method, and it's on policy learning. So we can also call it online learning. The way to construct a dataset for this approach is similar to STAR. So we use a problem, feed the problem to the model, and then it proposes a solution. And then we input the problem, the solution 1, and self-correction prompt to the LLM, and it gives a solution 2. The only difference here is that the LLM is initially the off-the-shelf LLM, but during training, we use the updated LLM to generate a dataset, rather than always using the original off-the-shelf LLM to generate a dataset. So this is why it's called on-policy or online learning. And another major difference from SFT is the training objective. So with reinforce, we try to maximize the reward. So here, the reward corresponds to the first solution and the second solution. If they are correct, they are given a positive reward, such as +1. And if they are wrong, it could be 0 or -1. So we maximize the log likelihood of tokens for the correct solution, and minimize the log likelihood of tokens for the wrong solutions. And the second term is to minimize the KL divergence between the model that is being trained and the reference model. So the reference model is the initial model. The initial off-the-shelf model or new model is trained from. So this is to prevent the collapse to trivial outputs, because the reinforcement learning training objective often leads to collapse in practice. So we want to keep the behavior of the trained model close to the reference model. And then let's look at how it performs. So these two figures show the training results. Currently, we will just look at the multi-turn baseline, that is the reinforced algorithm we just talked about. And the solid line is turn 2 solution, and the dotted line is the turn 1 solution. And the x-axis shows the training fraction. That means the training progress. So it wants to show how the model behaves as training progresses. And as you can see, as the training progresses, the accuracies of turn 1 and turn 2 are both improved. However, on the right image, you can see the training progress leads to the different answer frequency, which is the y-axis. That means the frequency that the second round answer is different from the first round answer. It tends to decrease. So the training progresses and the difference drops. That means the model quickly learns to not change its answer in the second solution. This means the raw, or let's call it vanilla reinforce, doesn't work. And here comes the proposed method called SCORE. It is a two-stage training regime. So here is the training objective of the first stage. We remove the reward for solution 1 and only have the reward for solution 2. And the second term, the KL divergence, is only applied to solution 1. So this means we want the model to generate a similar solution 1 as the reference model, and we also reward model for generating a correct solution 2 and penalize the model for generating a wrong solution 2. Okay, so it encourages meaningful corrections in Y2, that is solution 2, and penalizes it when it doesn't. And we ensure that the first round is similar to the reference model, so that it doesn't encourage the model to improve the first round solution and not encourage to generate a wrong first solution either. Then in the second stage, we want to reward the model for generating correct answers in both rounds. And we also keep the model similar to the reference model in both rounds as well. But the difference here from reinforced is that we have one bonus reward for successful correction. That means if the first round is wrong and the second round is correct, then we reward the model. So here in the second stage, both solutions are rewarded for correct answers, and we try to keep the behavior close to the reference model, and we have bonus reward for the self-correction behavior. Yeah, let's look at the results. So back to the image as well. On this image, we see that the training iteratively on stage 1 and stage 2 consistently improved the model's accuracy on the training set. And there is a large gap, you can see a larger gap between the solid line and dotted line comparing with the multi-turn baseline. And on the right, you can see the stage 1 of SCORE method improved the situation of the decrease in the different answer frequencies. It is better than the multi-turn reinforcement learning baseline. And here is the table showing the performance of the method on a dataset called math. So this method is compared against the STAR with supervised fine-tuning on STAR and pair SFT and the baseline model. And the self-refine approach, that was not a training approach, but was only based on prompting methods to encourage self-correction. So as we can see, this self-refine has a drop of accuracy on the second round solution. It is consistent with previous results. That means only prompting the model to correct errors in the first solution will make the model mistakenly revise the first solution. And with star plus and pair SFT, there is a small self-correction improvement, and with square method, there's a larger one. So it's 4.4 overall. However, it's still not quite large. It's still just a limited self-correction rate. Alright, so that's the gist of this paper. There are some more details you can see by reading this paper. Okay, now let's summarize the pros and cons of the paper. So the first pro is that it shows both successful and failed strategies to instill self-correction behaviors into LLMs, and it is backed by rich experimental evidences. And there are some limitations. First, the proposed approach is limited to only one round of correction, and the practical use of this method is unclear, as the correctness of the first solution is unknown, so we don't know whether we need the second solution. And the improvement over reinforce is still limited. As you can see on the math dataset, there is only a 4.4 improvement. Okay,